Now that we've learned about reciprocal functions, we're going to take that idea one step farther. So instead of having just a function that's in the form of a fraction, where we have a very simple constant value over a variable, we're now going to take each of these parts of the fraction and make them more complex polynomial functions. And even though one would be considered polynomial and x by itself is a polynomial, we're now going to build off of these two particular parts in the numerator and denominator. So a rational function is any function where a polynomial is written over the top of a polynomial. Now, with so many polynomial functions to choose from, you get a larger variety of graphs whenever you have rational functions, and so there's a little less consistency here that you're going to notice. And so we're going to be looking for a few major parts when we're dealing with these rational functions. And so if you take a look down here at some of the examples that are given, you can see three types of things that can happen. In this first one, you can see it's a continuous function, and the way we know that it's a continuous function is if you look at the denominator, x squared plus 1, if there is no number that would make that equal to 0, then there's no place that the rational function is going to be undefined. And if there's no place where the rational function is undefined, then it's simply a continuous function. And you can see by the graph that it never stops in any given place. So those are some more basic examples. Pretty easy to run a t-chart on that and just come up with all of the points on the function. And of course the domain would be all the real numbers. Now, on the second one, in the middle function here, you can see that the x plus 2's on both the top and the bottom can cancel out. Now, when this happens, this is what we call removable discontinuity. And what happens here, anytime you have a removable discontinuity or a point discontinuity, it creates a hole in the graph. And so if you have a factor that is canceled out, you know that there's going to be a hole in the graph. And again, domain is all real numbers except for the value of that hole. In this case, it's -2. Now, if you look at the third example, you see that the denominator does not cancel out with anything on the numerator, but there is a value that makes the function undefined. And so in this case, we're going to create an asymptote. When we create an asymptote, that's infinite discontinuity, or what we would call non-removable discontinuity. And so whenever you start to graph or observe these rational functions, the first thing you're going to look at is, are there any values that make this domain undefined? And if there are, can those values be canceled out with something in the numerator? Now, the only way that you're going to be able to find that out quickly is by factoring all the parts of the numerator and denominator. So if you're not comfortable with factoring back from the quadratics unit, you're going to need to do a little review on that, because you will be doing quite a bit of factoring in this given unit. So those are your three basic examples. Now, that doesn't mean that all your graphs are going to look like these three graphs. Those are just the three samples of discontinuity that you could end up dealing with. So if we move down here, we can see sample problem number 1. We've given you 3 problems here, and we're just asking you to figure out what are the points of discontinuity, the domain, is it removable, non-removable, and what are the intercepts. And so I'd like you to take some time here and do parts A, B, and C. The first thing we're going to do in order to figure this out is we're going to go ahead and factor the denominator and get a simplified version of this. And the first thing that we notice is there's no factors that can be canceled out. So this is non-removable. And we know non-removable is going to create an asymptote for us. Now we need to figure out where those asymptotes are. And in particular, these are vertical asymptotes. So the vertical asymptotes are going to be where it would make the rational function undefined. So in this case, 3 would make that a 0, and 1 would make that a 0. So we can say that we have vertical asymptotes at x equals to 3 and x equals to 1. Now, it asks what's our domain. Our domain is going to be all real numbers except x cannot equal to 3 and x cannot equal to 1. And so it's pretty clear that whatever our vertical asymptotes are, those are the points that are excluded from the domain. Okay, then the last thing it asks us are what are the intercepts. And so to come up with the intercepts, you would just simply use zeros, just like we did way back in linear functions. You just plug in a 0 for all the x's, you plug in a 0 for all the y's, and then you can figure out what your intercepts are going to be. And so if we did that, by looking at the graph, you can see that it looks as if it's never going to cross the x-intercept, and it looks like it crosses the y-axis at 1. And if we plug that information into the given function, we would see that that would be true. And so our y-intercept is 0, 1, and there is no x-intercept. Okay, so that answers the first one. Let's take a look at B and C here. X squared plus 1 is the denominator. There are no values that we can use to make the function undefined, so that's going to tell us that it's continuous. So there are no points of discontinuity, removable or non-removable, so no vertical asymptotes, no holes. So now we know that our domain is all real numbers. And again, if we were to either plug zeros or graph the function, you would see that we have a y-intercept of 0, -5, and that there is no x-intercept. Alright, so that one was rather easy. If you notice, anytime we have a continuous function, it's a little bit more straightforward. And then lastly, again, for this one we need to factor. And you notice that we have some removable discontinuity here. And of course, you notice that the simplified function x plus 1, if you graph this, it's going to look like a line, even though there's a quadratic in the numerator. But since it's removable, what that's going to do is it's going to look like a hole, and there's going to be a hole where it's undefined. In this case, x equals to 4. So that's where the hole is going to be. Now the domain is going to be all real numbers except x cannot equal to 4. Now keep in mind, on MathXL, it may ask you to do this in interval notation, so that'll have you recalling interval notation from an earlier unit. And now we need to know the intercepts. Again, you could plug zeros for the x's and the y's to come up with the intercepts, and you can also look at the graph. Now you can see in the graph we have a line that looks as if it's going through 0, 1 and -1, 0. And the thing about this graph is that you'll notice the shortcoming on the graphing calculator is it does not show the hole that we know to be at x equals to 4. So if we went to x equals to 4 and we tried to find that, the graph will not show it us on our graphing calculator. And so we have, for our intercepts, 0, 1, and we have an x-intercept of -1, 0. Alright, so there's a first good example of dealing with rational functions.